Okay, sit down and shut up. I've got one announcement. You may have seen these glorious T-shirts which the helpers are wearing. We've got wonderful Fisher equations on the back. The company who makes them is prepared to produce more. We don't quite know what the price is, something between £9 and £12. If people are interested in receiving, buying, I'm not going to give them away, buying one of these T-shirts, just send me an email and we can see what we can do about it. You can send the money, you won't necessarily get a T-shirt. Second thing is, what the hell is it? It was something important, and now I've forgotten it. It may or may not come back to me. These things get a little more frequent as time goes to infinity. All right, so I'll hand it over to Kay, who's going to chair the session before the tea break.
Good afternoon, everybody, and welcome back to the continuation of this Fisher meeting. I represent the Genetics Society here today, and we're delighted to have partly funded this meeting. So I'd like to introduce our first speaker this afternoon. It is Himani, and she's going to talk to us about introgression under the infinitesimal model with linkage. So this is a continuation of Nick's speaking this morning, the things he spoke about this morning. So welcome to Himani. Thank you.
So I'm going to talk about how selection on many infinitesimal variants that are linked affects introgression in a rather simple model scenario. So the motivation, the sort of renewed focus on infinitesimal frameworks comes in part from GWAS, which suggests that many traits are highly polygenic. And in particular, there's this observation that the proportion of variants of traits such as height that is explained by individual chromosomes is proportional to the length of the chromosome. And so this suggests a genetic architecture in which causal variants are more or less uniformly spaced across the genome, and in which there are many causal variants per chromosome. So it becomes important to extend sort of the infinitesimal framework and go beyond freely recombining loci and really consider linkage. So a sort of simple way of thinking about linkage in this context is to consider that there are some large number of loci that are, let's say, uniformly spread across a block, and there is a rate of recombination R between adjacent loci, and these loci contribute additively to some trait, and they have some average contribution, and they have some variance. So the infinitesimal limit is one where you take the number of loci to be very large and the rate of recombination to be correspondingly small, and also the variance of contributions of individual loci to be small. And at some point, the only quantity that matters really is this, so in this large L limit, the only quantity that matters is the genic variance per unit map length, which is the ratio of this variance to the recombination rate. And what I mean when I say that's the only quantity that matters is that if you have a sort of block of some map length which is associated with some trait value of the additive trait, and if you ask that what is the sort of trait value associated with different descendant fragments, different short descendant fragments, then these have a distribution which only depends on this, the genic variance per unit map length. And this is really an old result, and it comes from sort of central limit kind of arguments. So what I would like to do is to ask what happens when, in a very simple introgression scenario, where one such introduced block with a large number of infinitesimal or very weak effect variants. And this block is introduced into a recipient population that is genetically homogeneous. So in this talk, I'm also going to focus only on one case where the trait value associated with this introduced block is the same as the trait value associated with the blocks present in the recipient population. However, if you look at different descendant fragments of this block, then these, of course, could have a range of trait values. It's just that they add up to a particular trait value here. And the sort of range of trait values here is again determined by V0, the genic variance per unit map length. And I'm going to consider introgression under directional selection, so where all these infinitesimal variants add up to some trait value, and that trait is under directional selection. And so the question really becomes that, as this block splits up into smaller and smaller fragments, and these are presumably associated with weaker and weaker effects. So in the long run, can you see anything which is really different from neutral introgression? And if yes, then what sort of are there general criteria which we can pose, which sort of would explain why certain fragments or why certain individual variants introgress with high probability? So it's sort of useful to get some intuition about this process by looking at snapshots. So on the x-axis, you have map position along the introduced block. On the y-axis, I have I have individuals who carry at least some fragments of this introduced block after 20 generations. Each such horizontal line represents a descendant fragment, and the colored bit represents the fragment that they have inherited from this one introduced block. And the colors represent the trait values associated with individual fragments. So as you can see in this example, most descendants have a block that actually makes a negative contribution to trait value, so it's deleterious under directional selection in this case. But after 80 generations, the descendant fragments are, of course, smaller, but they're also predominantly positive, so green represents positive fragments here. And so one imagines that this happens because recombination manages to separate out beneficial bits that are embedded within these larger deleterious blocks. One can look at a different snapshot, and something similar happens here, but in this example, the introduced block happens to contain a rather strongly beneficial fragment so that introgression is faster, and you have 700 individuals at 80 generations who carry at least some fragment of the introduced block, as opposed to 80 in the previous example. One can, of course, go beyond this looking at snapshots and consider the average dynamics of this process. And so the key point here is that there's a qualitative difference between neutral introgression and between introgression under some kind of directional selection. So the dashed line represents how the number of descendants who carry at least some part of the introduced block increases with time if there's no selection. And here you have a sort of block of 25 centimorgans. The green, blue, and red lines represent how the number of descendants increases under this kind of infinitesimal selection. And as you can see, there's a linear spread for neutral introgression, but actually there's a strong deviation from the linear spread. There's, in fact, an exponentially fast introgression at longer times when there is infinitesimal selection. And it's faster if the strength of selection is higher, or if the genic variance per unit map length is high. So of course, the reason for this kind of exponential spread is sort of hinted at by the snapshots, which we saw in the previous slide. If you consider, so imagine that the introduced block has a fragment of map length y and trait value z. Then this fragment is amplified by selection at some rate which is proportional to beta z, where beta is the strength of selection, and it's split by recombination at a rate proportional to y. So this is going to this fragment is going to increase exponentially as a non-recombining unit as long as beta z is greater than y. And the key point is that even if you have a block that is neutral on the whole, and so that it has as many variants that make a positive as a negative contribution on average, and even if there's no statistically significant clustering of loci according to their effects, there is still sort of a range. You still have sort of fragments or stretches which are positive or negative, and the typical trait value associated with fragments of length y is really proportional to square root y. So if I plug this in, what emerges is that successful fragments have a characteristic map length, which is proportional to beta square v naught. And this beta square comes because we have assumed a neutral block, and not if the block had some selective advantage with respect to the native population, then it would actually be beta. So the key idea is that there are these successful fragments that emerge even when there is no statistically significant clustering of loci, and these are going to increase in frequency, and they're going to grow exponentially, in fact, and even they could also contain deleterious variants, and these are also going to increase in frequency. So in the last bit, I'm just going to try and apply this to the case of something which is not quite infinitesimal. So you have some 2,000 odd variants embedded on a 40 centimorgan block. And I'm going to ask whether we can say something about the introgression probabilities of individual variants on this block. And so one can, of course, do the maths, and it turns out that the key quantity for any of these variants is its expected growth rate, which is this beta z minus y value, or the rate at which a block grows intact, for the fastest growing block that contains this fragment. And it turns out that the introgression probability of individual variants shows a significant linear correlation with the expected growth rate. And it's worth noting that the expected growth rate is really a measure of linked selection, because it depends on the trait value of all variants within a characteristic linkage scale. And so there's a sort of high linear correlation, and one can also see that within blocks with the same expected growth rate, within variants with the same expected growth rate, that is, within variants that are all part of some fast-growing block, there is some differential introgression of the red dots, which represent positive effect loci, and the blue dots, which represent negative effect loci. So this is really so the picture that emerges is that there are two time scales, the early time scale being one which is dominated by linked selection and the exponential increase of certain blocks, and long time scales in which, if the population is large enough, there can be some kind of fine scale recombination that will separate out deleterious variants within a block. And it's worth noting that the correlation with the sort of own effect of the allele is quite weak. And in fact, if one looks at the top, at sort of variants with greater introgression probability greater than 0.5, about 10 or 15% of those are actually deleterious. Whereas if you look at here, expected growth rate is a very good measure of what can increase and what cannot. And if the block has a negative expected growth rate, there is sort of almost zero introgression probability. So maybe I will stop here and just keep the conclusions somewhere.
Thank you, Himani. Do you have any questions? I think she's quite happy that we don't have any questions.